Hi, my name is Eduardo. I'm a scientific researcher at Iguanova, and this is our paper, ReBaPL, Repulsive Bayesian Prompt Learning. So here we're fine-tuning CLIP. So CLIP is a vision language foundational model, and we're doing prompt learning, meaning we have textual prompts that serve for image classification. So let's say we're trying to classify cats from dogs. The main idea is that we're going to have a prompt in, let's say, a photo of a dog that's going to have a higher similarity to dog images than cat images. These prompts, these textual prompts, they are learnable, meaning they are variables that we optimize. And the idea is that a photo of is tunable. It's a prompt that we learn. Now, how is that done? Usually, you have a training set that you optimize the likelihood on it. But when you do that, unfortunately, CLIP overfits to the base classes because we are in a few-shot learning scenario, meaning we don't have that much samples. Now, what we want is we want to fine-tune on the base classes while retaining the performance, good generalization to the novel classes, meaning the classes that we don't see during training. Now, how we do this? We propose a plug and play method that's based on Bayesian learning. So instead of having a point estimate, we're going to have a Bayesian posterior. So instead of one single estimate, we're going to sample for this Bayesian posterior through MCMC methods, for instance, longitudinal dynamics. The main insight here is that the Bayesian posterior is a multimodal because you can have many different prompts that suffice the same task. For instance, a photo of a dog is a plausible prompt for classifying dogs, but at the same time, an image of a dog, a figure of a dog, so on and so forth. So our main idea is that we're going to need to explore the modalities of this prompt, and we do so through repulsive force. So in a nutshell, that's our architecture. We have the clip shown on the left, and the main idea is that on top of the MCMC dynamics that you see in these equations, we add a repulsive force between the prompts we already collected and the new prompts. So you can think of that image. Of the image, we have the past prompts in as a blue star, and we have the orange star that gets repulsed away from the blue star. The orange star is the new prompt. So again, this is a plug and play, and we collect many samples from this posterior based on these MCMC dynamics. So why does it work? Actually, you have the negative log likelihood that attracts the prompts to the high density regions of the posterior, and you have this another potential that repels from the old prompts. The idea is that you're going to visit different areas of high density of this posterior. Now, as I said, this is a plug and play method. So we plug over existing methods of prompt learning, most notably Maple and MMRL, which are state-of-the-art methods. The idea is that our method, our extension, let's call it like that, improves performance while not decreasing on particular datasets. Most importantly, we have strong cross dataset transfer of prompts, meaning you tune the prompts on one dataset and then transfer to others, and also domain generalization where you have distributional shift occurring. This proves that our method doesn't suffer from overfitting. So to recap, we have maximum likelihood estimation that leads to overfitting. We use Bayesian statistics to counter that. We use repulsion to explore the multiple modes of the posterior distribution, and our method is a drop-in extension. You can check our paper on arXiv and our code on GitHub. Thank you very much for your attention.